This is the first of a two-part presentation on exploring solid similarity. So these are solids that are similar to each other. So what are similar solids? So similar solids are solids that have the same shape, but they have different sizes. So if you remember in our studies as we've gone through geometry, we've looked at congruence of figures like polygons, and then we had similarity of polygons. So similar polygons were same shape but different size. Same deal with solids. Solids have the same shape but the different size. And when we compare them and we get a reduced number for all the major dimensions of them, we get a scale factor. And that scale factor is going to correspond with any measure of a solid. So like the radius, diameter, height, width, length, all of those major lengths of solids are going to correspond at the same scale factor. So similar solids are solids with the same shape but different size. So it's kind of like, honey, I shrunk the solid. So how do we check for similarity? So if you remember, we had a side, side, side for congruence of polygons, and we had a side, side, side for similarity. Those had to be proportional, though, not congruent. And we have the same deal basically with solids. So if I'm going to check for similarity with solids, I'm going to check corresponding side lengths and see if they all reduce to the same number. If they do, then I have similar solids. So you're like, well, how do I check? So on the solid on the left, I've got dimensions of 3, 4, 8, and 5. On the one on the right, I've got 9, 12, 24, and 15. And it's like, how do I compare the numbers? So what I usually do is I just take the smallest ones first. So I have 3, that's the smallest number on the left, and 9 is the smallest number on the right. And I correspond them. So 3 to 9 reduces to 1 over 3. Then I take the next biggest number, which is a 4 over here, the solid on the left. And the next biggest number on the solid on the right is 12. And 4 over 12 is going to correspond with 1 over 3. Then I do that with the next biggest number, which is 5 here. And the next biggest number on the solid on the right is 15. And 5 to 15 reduces to 1 over 3. And then I do the same thing with the biggest number. So the biggest number here is 8. The biggest number here is 24, and these are the heights. And that reduces to 1 over 3. So all of the corresponding side lengths reduce to the same number, and it's like, okay, now find the scale factor. Well, everything reduces to 1 over 3, so the scale factor between the two solids is 1 over 3. So let's check a new example here. So again, I'm going to check the radii first. These are the smallest numbers. So I've got a 5 here, and I've got a 10 here, and 5 over 10 is going to reduce to 1 over 2. And now I'm going to check the heights. The height of this solid is 10. The height of this one is 15, and that reduces to 2 over 3. You'll notice the numbers are not the same. So 1/2 and 2/3 are not the same. So then the solids are not similar, okay? So that's a really big deal here. You can't find a scale factor if the solids are not similar. Now, as I told you before, like major lengths of a solid, like length, width, height, slant height, all of those are going to correspond to the same scale factor. When we're dealing with surface area and volumes, though, the scale factor is in play, but we have to treat that just a little bit differently. Surface area is the amount of area that's exposed in a solid. So like it's like the area of all the side lengths here. So the area here, the area here, the area at the bottom, and the two back sides here. That's surface area, okay? Because area is in square units, when you are corresponding similar solids, you need to square the scale factor, which means you square the top number and you square the bottom number. And then when you're looking at volume, like the amount that's inside of a solid, you use that scale factor, but you have to cube the scale factor. So you cube the top number and you cube the bottom number. So surface areas correspond at a square scale factor and volumes correspond at a cube scale factor. So let's take a look at this a little bit more in depth. So I've got two cylinders here. I've got the cylinder on the left, which has got a radius of 3. I've got the cylinder on the right, which has got a radius of 6, okay? So I'm just going to check the radii, the ratios here, and 3 to 6 is going to reduce to 1 over 2. Now if I'm going to check the surface area, so this is about the area that's on the outside of the figure, okay? Areas in square units, so I'm going to square the scale factor. So I square 3 and get 9, and I square 6 and get 36. And 9 to 36 reduces to 1 to 4, because 9 goes into 36 4 times. Now, if I'm going to take a look at the volume, like the amount of stuff that's inside the solids, you'll notice, you'll be like, well, 3 to 6. If you look at this figure, even though maybe the radius is double, the volume is like way, way, way bigger. Like there's way more than double the amount that's in the small cylinder. So we cube the scale factor. So we take 3 cubed. 3 cubed is 27. And then I take 6 cubed. And 6 cubed is 216. And that's going to reduce to a scale factor of 1 to 8, because 27 goes into 216 8 times. Now, if you look at the scale factors here reduced, okay, this is going to make sense, okay? The scale factor is 1 to 2. When I take a look at the area, I square both numbers. 1 squared is still 1, so it doesn't look drastically different. But 2 squared is 4. So this scale factor here of 1 to 4 is actually squared. It's squared of 1 to 2. And then I do the same thing with the volume. I take 1 cubed, and 1 cubed is 1, and 2 cubed is 8. So the volume is actually at a cubed scale factor, okay? So there's 8 of these little cylinders that'll actually fit in this, even though you might think it's only double. So let's try it in a real-world example so you can actually see how this works out, okay? So I want to find the volumes of these solids, and that should be pretty easy for you. It's area of the base times height, or if you remember back to probably middle school or elementary school, is length times width times height. But I'm just going to go area of the base times height. So 4 times 6 is 24. 24 times 2 is 48. So this small solid is 48 cubic units. Then I do the same thing with the solid on the right. So I take 8 times 12 and get 96. 96 times 4 is 384. So the volume of the big one is 384 cubic units. The volume of the small one is 48 cubic units. Okay? Nothing really special or spectacular here, but I want you to remember these numbers. Think in your head 48 and 384, because that's going to become a big deal here on the next example. So we're going to do this a different way. So let's pretend I don't know these lengths. I don't know the height, and I don't know the length. I just know the width here, okay? And I know all the ones of the big one. And I want to try to figure out the volume of the volume of the small solid, but I don't know these lengths. I can use the scale factor to help me find that, okay? So I just take the sides that I know. I know that the solid on the right, the only number I know is 6, and that's the width, and that's going to correspond with 12. So when I reduce those numbers, 12 over 6 becomes 2 over 1. So the scale factor between the two solids is 2 to 1, right? Then what I want to do is find the ratio of the volume. So I'm going to cube the scale factor. So 2 cubed is 8, and 1 cubed is 1. So this is 8 times as much volume as that one. Okay, so the ratio of the volume is 8 to 1. So I figure out the volume of the big solid. 8 times 12 is 96 times 4 is 384. So I set up a proportion. So the ratio of the volumes is 8 to 1. So give me 8 to 1 equals 384 over x. The reason why the 384 goes on the top is because it's got to correspond with the 8. So the big volume is on the top, the big volume is on the top. So I solve this proportion and cross product multiply, and I basically get 8 times x to get 8x. 384 times 1 is 384. Divide both sides by 8 and get 48 units cubed. So if you remember back in the previous problem, we figured it out. We got 48 units cubed here. But in the second example, we actually used the scale factor to find the 48 cubic units. And if you notice that you've got a 2 to 1 ratio in your like volume, okay, 2 to 1, cube it, it's 8 to 1, and I know this is 384. Can I just take 384 and divide it by 8 to get this one? And the answer is yes, you can absolutely do that. All right, so let's try to find it where we those other ones were pretty obvious, but here's one where it's not so obvious. I want to find the volume of the smaller cylinder. So I know the radius of the big cylinder is 6, the radius of the small cylinder is 3, and I already know the volume of the big cylinder. So I'm going to figure out the scale factor between the two cylinders. So I have 6 and 3, and that's going to reduce to 2 over 1. So the scale factor between them is 2 over 1. Now to figure out the volume scale factor, I'm going to need to cube that ratio. So 2 cubed is 8, and 1 cubed is still 1. And now I can set up the volume. So it's going to be 8 to 1 equals 3,200 over x. And then I cross multiply. And 8 times x is 8x, and 1 times 3,200 is 3,200. And I divide both sides by 8, and I get 400 cubic units. So the small cylinder is 400 cubic units in volume. Okay, let's take this in a little bit of a different type of example. So I'm going to kind of go backwards. Here I'm giving you the volumes, and I'm like, okay, what's the scale factor between them? So I have 1,000 inches cubed for the pyramid on the left and 216 inches cubed for the pyramid on the right. So I need to convert that to a side length ratio. So I have two ways I can do it, okay? I can convert these numbers to cubic numbers, okay? So 1,000 is 10 cubed and 216 is 6 cubed, okay? But you might not know that, okay? I happen to know it, but you might not know that. So you can actually use your calculator to figure this out. So you can actually take the cube root, you'll have a cube root button on your calculator, and take the cubic root of 1,000, okay, and you're going to end up getting 10, and take the cube root of 216, and you're going to end up getting 6, okay? And that reduces to 10 over 6, and then you can reduce 10 over 6 as a fraction to 5 over 3. So the scale factor between the two solids, or two pyramids, is 5 to 3. All right, so let's take a look at another example here. This one I'm going to have quite a bit of math work to do. So the two solids are similar, and the scale factor is 100 to 87. So this is 100 parts and this is 87 parts. So I'm going to need to square the scale factor to find the surface area first. So 100 squared over 87 squared. And then since I know the surface area and volume of the small one, the 87 squared is going to go on the bottom of this proportion to solve the surface area. So I'm going to cross product multiply. When I get 100 squared times 51.84, I get 518,400, and 87 squared is 7,569. And then when I divide 518,400 by 7,569, I get 68.49. Now to do the volume, I'm going to have to cube the scale factor. There we go. So 100 cubed over 87 cubed. And again, I know the small one, so the number in the proportion has got to correspond with the small one. And then I'm going to just cross product multiply. 87 cubed is 658,503, and 100 cubed times 28.27 is 28,270,000. And when I divide that by 658,503, I get 42.93 cubic inches. So that's how I do this type of problem. All right, last example. So a store sells yarn in two sizes. One the size, the diameter is twice the other one. So if the small ball is $2 and the large ball is $8, which one's the better deal? So you'd be like, well, wait a second, the diameter is twice the size, so the small ball should be $2 and the big ball should be $4. So clearly the small ball is the better deal. But let's look at this a little bit more in depth, okay? So first of all, when you're selling yarn, it's volume. It's a three-dimensional figure. So we need to figure out the scale factor. So if one is 2 times the length or 2 times the diameter of the other one, the scale factor then is going to correspond at 8 to 1, okay? So a ball of yarn that has twice the diameter actually has 8 times the volume. And then figure out the ratio of the price. The price is only 4 to 1, but you're getting 8 to 1 more volume. So in this case, the big ball is a much better deal. And oftentimes, if you order a pizza, like if you're getting like a 10-inch pizza for $5 and a 16-inch pizza for $7, like the big pizza is going to be a way, way better deal, even though on the surface it might not look like that great a deal. All right, so in honor of similarity of solids, I've given you 2 similar assignments. I have a big assignment here on the top, and I have a small assignment here on the bottom. And you can do either one if you like to solve your handing in for an assignment. But on Wednesday, I want you to do page 786, problems 1 through 10. Excuse me. On Thursday, I want you to do questions 11 through 16. And then on Friday, do questions 19, 26, 27, and 32. When you have all 3 of them done, then you can send them to me in one email, and that will count as an assignment. So that is your presentation on similar solids. I hope you found it helpful.